Hello guys, welcome to Kobe Smart Nook. Today too we are going to look at another concept, and that is non-homogeneous differential equations reducible to homogeneous equations. Indeed, there are certain differential equations that are non-homogeneous, but with some transformations these equations can be found to be homogeneous. Without wasting time, let's consider the following equation. So we have this differential equation: dy dx equals a1x plus b1y plus c1 all on a2x plus b2y plus c1, where this form of non-homogeneous differential equations are in two cases. In case 1, the numerator and the denominator are distinct. What this means is that the coefficients of the x and y in the numerator and denominator are different in the case 1, and the equation cannot be reduced to simple proportionality. We cannot do anything about this equation. In that case, there is no common factor between the coefficient of x and y values of the numerator and denominator. An example of such equation is dy dx equals. When you consider this, you can see clearly that everything here is distinct, different from each other. In the x, coefficient of x is 1, coefficient of x at the denominator is 2, coefficient of the y at the numerator is -3, coefficient of the y at the denominator is 0, and then the constant 2 is what? Different. But here the focus is on the what? The coefficient of the x and the y, but not the constant. So when you find a differential equation of this form, then this is the first case, and it has a distinct way of solving, where we will set the constant terms to be 0 for it to become homogeneous for us to solve. We will later look at examples on that. Then we have case 2. In this case 2, the first thing that we need to consider is that the determinant of the coefficient of the x and y in the numerator and the denominator is 0. So it means when you try to find the determinant of this particular coefficient, it gives us 0. So a1 b1 a2 b2, when we multiply a1 b2 minus a2 b1, is supposed to give us 0. Take a real example. In this case, dy dx equals 2x plus y minus 1 on 4x plus 2y minus 5. So let's try to find a determinant of the coefficients of x and y in both the numerator and denominator, and that gives us 2 1 4 2. And you can see when you multiply this side we are getting 4, minus when you multiply this side we are getting also 4, and that gives us 0. So when we have non-homogeneous differential equation of this form, where the determinant of the coefficient of x and y at the numerator and denominator gives us 0, then it is also another form. Notwithstanding that, another thing that you need to note about the second case is that one variable is a constant multiple of the other. That is, when you look at the coefficient of the x and y at the denominator, you can see that the denominator part is the constant multiple of the numerator. In other words, when you consider the differential equation, this, you can see here 2 is common over here. So when we factor 2 out, we are getting 2x plus y, which is the same as what we have at the numerator. So this implies that the terms a2x plus b2y in the denominator is a constant multiple of a1x plus b2y in the numerator, which means a2 equals ka1 and b2 is also kb1. When we're able to identify this in the second case, this is another way or another form that we can also consider. It also has a special approach in solving it. We will look at examples on that, and that will help us to understand better. Example 1. Solve the differential equation dy dx equals x minus 3y minus 7 on x minus 4. So as you can see, this is a type of differential equation where the x and then y has nothing in common. They are not related, they are not linearly dependent. Hence, we need to first of all change the variables x and y, and that will help us to transform this equation to homogeneous form. Solution. So first, we are going to change the variables for x and y. So we say let the x variable now becomes x1 plus h. Please take notes. And then the y also becomes y1 plus k. You know that this k and h are constants. Let's replace x1 plus h and y1 plus k into the function. So when that happens, you can see that now the variables are no more x. They are now x1. And then the y variable is no more y, it's now y1. So this needs to also change. So now it means our dy dx now becomes dy1 dx1 equals our x is now this. So we are going to get x1 plus h minus 3. Then the y is y1 plus k minus the 7. All on our x is x1 plus h minus 4. Now let's group the constants h, k, and 7 to one side, and then the variables also in front. So our y1 dx1 now becomes x1. So when you try to expand this, you can see that this becomes negative 3y, and then plus h, this h, and then this will also give us minus 3k minus 7, all on x1 plus h minus 4. Don't forget that initially I made you understand that if this constant term c1, c2 is set to be 0, then the other part of the differential equation becomes homogeneous. So we're going to do the same thing over there. So you can see that h minus 3k minus 7 are all constants, and also h minus 4 is also constant. So we are going to set this part to 0. So the next stage, we set the constant part h minus 3k minus 7 to 0, then h minus 4 also to 0. This is simultaneous equation, so we need to solve for h and k. It is clear here, you can just use your calculator to find the answer of h and k, but here it is clear that h is 4, our h is 4, and our k, if h is 4, when you put 4 over here, k will be also negative 1. Now if this is 0 and this also is 0, now our dy1 dx1 also becomes x1 minus 3, this is 1, 3y1 on x1. This is homogeneous differential equation. So we say let's y1 equals ux1. Everything is in terms of y1 and x1. Take note of that. Let's substitute that here. y1 dx1 equals x1 minus 3. Now the y1 is this, so ux. So we are going to factorize as usual the x1 out. So our y1 x1 equals, here will be 1 minus 3u on our x1. So x1 cancel x1, our dy1 dx1 becomes 1 minus 3u. Now that we have this, from y1 equals ux1, we can differentiate this with respect to x1, and that will give us dy1 on the x1 equals u plus the u dx1. In this case, this dy1 dx1 is equal to dy1 dx1, so we can equate the two. So equating the two, let's label this equation 1 and this equation 2. So equation 1 equals equation 2, 1 minus 3u equals u plus the u dx1. Let's move this to this side. We are getting 1 minus 3u minus u equals x1 du dx1. And then when you simplify this side, that gives us 1 minus 4u equals x1 du x1. Separating the x1 on x1 equals the u on this one also become the denominator for u. We can integrate. When we integrate this, we are going to get an x1. Then also when we integrate this part, we should take in, let's w equals this, the w equals negative 4 du. The u becomes dw on 4, negative dw on 4. Substituting everything back. Where this is w, so become w. So factorizing, so we are going to get negative 1 on 4 integral of 1 on w dw. And this is why negative 1 on 4 ln w, which is equal to negative 1 on 4. W is the same as that. Integral of the x1 on x1 equals ln x1. Let's add the ln c to this side equals, we had negative 1 on 4 ln of the denominator 1 minus 4 u. Moving the negative 4 to this side and putting this together, we are going to get ln c x1 by negative 4 equals ln 1 minus 4u, of which we can get ln cx1 power negative 4 equals ln 1 minus 4u. Taking antilog of both sides, we are getting cx1 power negative 4 equals 1 minus 4u. But we know that u is equal to y1 on x1. If that's the case, cx1 power negative 4 equals 1 minus 4. Substituting the y1 on x1 into the u, that gives us y1 x1, which can further be written as simplifying this side, but we shouldn't forget that we stated that x is equal to x1 plus h, of which when we find the x1, we are going to get x1 is equal to x minus h. Also, y equals y1 plus k, which implies that y1 is equal to y minus k. Notwithstanding, we were able to find h to be 4 and then k to be negative 1. So substituting those terms in here, our x1 now becomes x minus 4, then our y1 becomes y plus 1, which gives us the final answer as, when we put it into this, give us the final answer as c brackets x minus 4 power negative 4 equals x minus 4 minus 4 by y plus 1 all on x1, which is this. That's x minus 4, and that is that.